A leaky 10-kilogram bucket is lifted from the ground to a height of 11 meters at a constant speed with a rope that weighs 0.8 kilogram per meter. Initially, the bucket contains 33 kilograms of water, but the water leaks at the constant rate and finishes draining just as the bucket reaches the 11-meter level. Find the work done. Use 9.8 meter per second squared for gravity. We start by first drawing a diagram. Let x be the height in meters above the ground. We assume that initially the bucket is located on the ground. It is filled with water and it is being pulled up with a rope. The remaining mass at different level xi's are not constant. And that is because even though the bucket has a constant mass of 10 kilogram, the mass of the water inside the bucket is not constant because initially the mass of the water is 33 kilogram, but when the bucket gets all the way to the top at the 11-meter level, the mass of the water is now 0 kilogram because the water finishes draining completely when the bucket reaches the 11-meter level. Also, the mass of the rope is not constant because initially the length of the rope is 11 meters, but when the rope gets to the top, then the length of the rope is 0 meter. Since the mass is not constant, we will consider slicing the mass so that we can lift the mass at each distance delta x. At any level xi, the work is the force times the distance. The distance is delta x, the force is the mass times the acceleration, which is the gravity. The distance is delta x, where the mass at any level xi is the mass of the bucket plus the mass of the rope plus the mass of the water remaining. The mass of the bucket is 10 kg regardless of where xi is. The mass of the rope is the mass of the remaining rope at the xi level. The remaining part of the rope is therefore 11 minus xi, and the rope weighs 0.8 kg per meters, and there are 11 minus xi length left. For the mass of the water, initially, if x is 0, the mass of the water is 33 kg, and when x is 11, the mass of the water is 0 kg. Thus, the rate at which the mass is decreasing is 0 minus 33 over 11 minus 0, which is minus 33 over 11, or minus 3. This is the rate at which the mass of the water is decreasing, minus 3 kg per meter. We start with 33 kg of water. When the water gets to the level xi, 3 xi kilogram is gone. And so the mass of the water at the xi level is 33 minus xi. Notice that we could obtain the same expression with positive 33 over 11 times 11 minus xi. At the level xi, the remaining mass is therefore 10 kg for the bucket, 8.8 minus 0.8 xi for the rope, and 33 minus 3 xi for the water. 10 plus 8.8 plus 33 is 51.8 minus 0.8 xi minus 3 xi is minus 3.8 xi. The work at the xi level is 51.8 minus 3.8 xi times the gravity, which is 9.8, times the distance, delta x. The total work is the sum of all of these wi as I go from 1 to n. 9.8 times 51.8 minus 3.8 xi times delta x. And as n go to infinity, we obtain the definite integral from this Riemann sum, 9.8 times 51.8 minus 3.8x. We drop the subscript I and the delta x becomes dx. We add up all of these slices from x equals 0 all the way to x equals 11. So the lower limit of integration is 0 and the upper limit of integration is 11. 9.8 is a constant. We can put 9.8 in the front of the integral, and we find the antiderivative of 51.8 minus 3.8x. This should be quite simple. The answer is 3,331.02 joules.